Yes. Welcome to this session of refraction of light. So basically, refraction, we can see it is a bending of light. This phenomenon involves bending of light. It happens especially when light travels from one medium to another medium. Okay. So we can see over this example over here that a ray of light is entering from air. It enters a glass block and then it emerges, the ray of light emerges out from the glass block also. So from air to glass and glass to air, in both these situations, when this transition is happening, we see there is a bending taking place. The main cause of bending is that the light takes different speed. Light travels with different speeds in different mediums. So in the speed of light is different in air compared to speed of light in glass. And then again, when it comes out, again the speed of light is different. So one of the core reasons of bending is because of different mediums, light has to travel with different speeds, and because of change of speed is one of the main core reason for bending of light taking place at these 2 points at the interface. We can say the interface between air and glass and air. At the interface between two mediums, this bending is normally taking place. We can see that various phenomenons or places where we could see different instances of refraction taking place. Because of refraction, we can see that when a stick, okay, a straight object, when it is kept inside, half submerged in water, half in air, when we see this object from an angle, we find that the stick has broken or the stick is bent, and this particular feeling we get it because of actually the portion of the stick which is there inside the water, and compared to the portion of the stick which is in air, because of the nature of bending of light, we feel actually the stick is bent. Actually the stick is not bent. Physically the stick is as straight as thing, but we feel because of a view and bending of light phenomenon, we feel the stick is bent. Again, this is another phenomenon where we can see that a pencil we feel that it is broken down, because again a part of the pencil is submerged in water and a part is protruding out. Also, the instance where we can see that if there is a coin or an object inside a basin of liquid, we find that because of this refraction, the coin is comparatively above than the actual position. Whatever the position of the coin, we feel that the coin is actually, we feel the coin is little above than the actual position. So we have an actual position, there is something called as an apparent position. So this is all because of bending of light taking place because of change of medium, and because of change of medium, there is change in we can say change in the speed of the light in different mediums. Another phenomenon that we can see is when we look in uh, a bucket of water or in a container of water, we sometimes feel that, we most of the time feel that the bottom of the tank or the bottom of the uh, container of water is raised. This dotted line is the raised position, and the PQ is the actual position, actual bottom of the tank. PQ is the actual bottom of the tank. P dash Q dash, this dotted is the raised thing that we visualize when we see, when we try to see or look inside the water container. So this is like the apparent depth, we can say, the dotted line from the level, water level to this dotted line is the apparent depth, but the real depth or the actual depth is different. So the apparent depth is smaller than the real depth, and that is the reason we say that the water seems to be raised up, or we see that the bottom has been raised up. So this is the effect of the glass slab. If you happen to find a glass slab, if you keep it on, no, it's a glass slab, so it is transparent actually, but it has its own thickness. And what we find over here is if you place it on a written material, so the written material which is not covered by the glass slab is of the same size, but the portion of the written material which is covered by the glass slab, you will find it etched. You find it is raised and it is little large in size. Again, this is because of refraction. So this is refraction in day-to-day phenomenons, this one and this one. And this is what is actually we can say the laws of refraction, or actually the phenomena which are taking place when light travels from rarer medium to denser medium. The example over here is air to glass. Air is rarer medium, glass is denser medium. Rarer and denser, how do you differentiate? It is based on something called as optical density. So based on the optical density of the object, of the material of the object, we can say something is rarer or denser. The greater the optical density, we say it is more denser. Okay, not the physical density, it is called as optical density, please. So air to glass, what happens? That is rarer medium to denser medium. When light is incident and it reaches a point, okay, at the point of incidence, we can see that the light ray has bended towards the normal. NM is the normal, AO is the incident ray, OB is the refracted ray, and we can find over here that the refracted ray is bent towards the normal NM. So from rarer to denser medium, it bends towards the normal. The opposite happens when you're going from denser to rarer. Example over here is glass to air. Again, rays incident, AO, NM the normal, and we can see that instead of being in the same angle, it is bending away from the normal towards the x-axis, we can say. So the refracted ray is moving away from the normal. Therefore, we say when air travels from denser medium to rarer medium, it bends away from the normal. The last case is a case when the ray is incident perpendicular to the surface, which makes it the angle of incidence as 0. Please remember, the angle of incidence, the angle of refraction, all are measured with respect to the normal. And since it is measured with respect to the normal, when ray is incident perpendicular to the surface, okay, so there is a surface and the ray is incident perpendicular to the surface, we say that the angle is 0. It may be perpendicular to the surface, the angle is 90, but the angle of incidence is 0 because the angle of incidence is defined with respect to the normal. And we see what happens. The light goes unbent. The light goes unbent and emerges the same way as it was incident. So the incident ray is 90 degrees to the surface, and the refracted ray or the emergent ray is also 90 degrees to the surface. Both angle of I is 0 and the angle of refraction is also 0 because both these angles I and R are measured with respect to the normal.
Sir,
Yes.
sir, in this case, then can we say that there is no refraction happening because the ray is going
Yes.
undeviated?
Yes. When
Okay.
there is bending only, then we can say refraction is taking place because refraction is defined as bending of light. It's a phenomenon of bending of light. So when
Okay.
a light ray is incident perpendicular to the surface, oh, so then there is no bending happening. So therefore we can say there is no refraction taking place. But then this
Yes.
all is covered for the transparent medium. We say overall this is refraction, but there is zero angle refraction here. Here there is a refractive angle. So it goes unbent. So in this case, at this particular point of time, we find that there is no refraction taking place. That is true. So the laws of refraction, of course, these are the rules of refraction. And this is the laws of refraction. The incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. Now, definitely there is a different bending involved in the incident ray and the emergent ray or the refracted ray. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction, which when put it like in the format, it looks like a formula. Okay. Mu is one of the, now some books use the notation as mu. Some books will use the notation as n or eta. So different notations can be there. Okay, but then please understand sin I upon sin R. Sine of the angle of incidence divided by sine of the angle of refraction gives you refractive index. Refractive index is always a constant for that particular medium. Now, this is the way we write it. 1 mu 2. Okay. Mu is the refractive index. 1 mu 2 means when light is traveling from medium 1 to medium 2. Refractive index of medium 2 with respect to 1. This is how you read it. Refractive index of 2 with respect to 1. So definition goes, the refractive index of the second medium with respect to the first medium is defined as the ratio of the sine of the angle of incidence. This is actually nothing but the translated version of this formula. The actual definition, refractive index of a medium is defined as the ratio of the speed of light in vacuum. Yes, we can see that. Yes. So refractive index is defined as the ratio of the speed of light in vacuum to the speed of light in that medium. And this is how we have written in a formula format. This is in the textual format. This is in the formula format. Speed of light in vacuum divided by speed of light in that medium, for which we are finding the refractive index. So the refractive index of a transparent medium is always greater than 1. It cannot be less than 1. Please remember that. It cannot be less than 1. Because the speed of light in vacuum, and what do you mean by that? Please understand, it cannot be less than 1. Matlab, it can be either equal to 1 or greater than 1. So you have to understand that speed of light in vacuum is more than the speed of light in medium. Because the speed of light in vacuum is more, the numerator is more than the medium. Therefore, it cannot be less than 1. Because for mu to become less than 1, the speed of light in the medium should be greater than the speed of light in vacuum, which is not possible. Speed of light in any medium is always less than that of the vacuum, and therefore we find that the refractive index will be never less than 1. We also have this case zoomed up. We have the different refractive indexes. We can see over here case of like vacuum and air almost goes together. We say the refractive index is almost 1. Next is water, around 1.33. Other liquids, we find these liquids are becoming denser, denser, denser. And then comes the solids. Ordinary glass, 1.5. See the crown glass, quartz, crystal, rock salt. Highest refractive index of any material, diamond. Okay. So these are the like. So we have the formula which connects, again, this formula was there in the chapter of sound also. We are using it in the chapter of light also. V is equal to F lambda. Velocity is equal to F lambda. So F for the frequency, lambda for the wavelength, V for the velocity. V equal to F lambda, very important to remember. Factors affecting the refractive index. Let's zoom it up again and just view it. So what is that? Factors affecting the refractive index. We can see that the nature of the medium, the optical density, of course. We saw that for vacuum, how much it was? Shraddha? Oh, sorry, Shija?
And
Yep. And for glass was around 1.5, highest for diamond 2.41.
diamond 2.4.
Yeah,
Yes,
so
sir.
that is the highest optical density. It depends on the temperature, external temperature. Temperature increases. So two things. One thing you have to remember: what are the parameters and how they influence it. So higher is the refractive index. That means, what do you mean by higher is the refractive index? The speed of light in the medium is lesser.
Yes, sir.
So more the optical density, the speed of light becomes lesser. Physical condition, increase in temperature, speed of light in medium increases. So directly proportional. Temperature increases, speed of light in medium increases. But what about the refractive index? The speed of light in medium is in the denominator. Please remember, refractive index general is defined as speed of light in vacuum divided by speed of light in vacuum divided by speed of light in medium. So
Yeah.
temperature increases, speed of light in medium increases, so refractive index decreases. So inversely related. Temperature increases, refractive index decreases. Color or the wavelength of light. We have seen that we'll be discussing this in detail also. And there's a chapter exclusively that human eye chapter is there. We know that white light consists of 7 colors with Goyer, and that also is discussed here. In other transparent medium, the speed of light is different for different colors. In a given medium, the speed of red light is maximum, and that of violet light is least. Okay, so please remember that also. This for the glass slab stuff. Okay, but then this is not clearly mentioned in the textbook, so I'm going to skip this.
Sir, actually, our sir taught us.
Okay. So here is a slide to study the refraction of light through a glass slab. So this PQRS is a glass slab. We just mentioned before that when a light is incident on a glass slab, this is air to glass medium. So PQ is called as the air to glass interface. That means it's a border, it's a boundary between air and glass. But now this is a transparent glass block. So definitely the ray of light, when incident like AO, it bends towards the normal. Air to glass, the rule is it bends towards the normal. So we see the refracted ray bend towards the normal. It reaches the other face, it reaches the other face of the glass slab, that is SR. And then again, it finds this interface or a boundary where there is glass to air interface, which is also called as glass to air, means denser to rarer medium. And according to the rule, when light passes from denser to rarer medium, it bends away from the normal. We can see this OB, which was already a refracted ray, which was bent towards the normal. Now, when it reaches this point, the point of refraction or angle, or the point of incidence, we see that the emergent ray BC is bent away from the normal than its usual path. Now, this emergent ray, we can extend it. At the same time, this AO, the incident ray, if you extend it, and from O onwards, we can extend it by showing the dotted line. We find that OD and BC are parallel to each other. They'll never meet because they are parallel to each other. So actually, if there was no refraction, then incident ray AO should go unbent. If there was no refraction, unbent, and it should have traveled this path of AD. But now, because of two bendings, one at the air glass boundary and again from glass air boundary, the final emergent ray is following the same angle as it was the angle of incidence. It's following the angle of incidence only. You can see the emergent ray and AD, the extended version of AO, both are actually parallel and pointing to the same direction, but they are displaced because they are parallel. They have a distance between them. That distance between them, the perpendicular distance between two parallel lines over here, is called as the lateral displacement. So the definition is there: the perpendicular distance between the original path of the incident ray and the emergent ray coming out of the glass slab is called as lateral displacement. However, again, if you are incidenting the light perpendicular to the air glass boundary, as the rule mentioned before, whenever light incidents on perpendicular, that is angle of incidence is 0, it just passes through along the normal. We can see it just passes as a straight line unbent. So AO unbent becomes OB, again glass air interface, again unbent, perpendicular to the surface, and then it goes unbent BC. So we find that AO, OB, BC all are on the same straight line and they appear perpendicular at the boundary, but with respect to the normal, they make an angle of 0. Emergent ray also making an angle of 0. Again, lateral displacement depends on the angle of incidence, the thickness of the glass slab, refractive index of the glass slab. As we see in the textbook NCERT, only the diagram is mentioned, refraction, how it takes place mentioned, the other details not being mentioned. This is for scope for further study. So these are the ways we use the notation. Like this is from incident ray from medium 1 to medium 2. So this was a case where rarer medium to denser medium, we can say the light ray is bent towards the normal. Notation wise, how you write it? V1 upon V2, medium 1 to medium 2, right? The light is traveling from medium 1 to medium 2, velocity of light in medium 1 upon velocity of light in medium 2. Written as notation wise 1 and 2, like that. Okay, they use the notation here 1 and 2. This is actually the textbook notation 1 and 2. Okay. In the previous example, I used the alphabet mu. Here I'm using N. Okay, so whichever is there in the NCERT, you can use the same notation. 1 and 2 actually indicates refractive index of medium 2 with respect to 1. This is how we read it. Refractive index of medium 2 with respect to 1. Also refractive index when traveling from medium 1 to medium 2. Here we can see the reverse happening. Light is incident from the medium 2 and then it is going to medium 1, which is a rarer medium compared to the denser medium. And therefore we can see that the refractive ray is actually bending away from the normal. Actually, if you see, these two materials are same. Medium 1, medium 2 here and the medium 1, medium 2 are the same over here. Therefore, when you incident the ray equal to the angle of refraction over here, angle of incidence over here is equal to the angle of refraction, it actually follows the same reverse path. That means here the angle of incidence in this case, because we are inciding the light from medium 2 to medium 1, the angle of incidence is equal to the previous case angle of refraction. And the angle of refraction over here is equal to the previous case of angle of incidence. However, formula wise, we write as 2 to 1, refractive index for 2 to 1 or refractive index of medium 1 with respect to 2. And since the first medium was medium 2, from medium 2 it is moving to medium 1. Therefore, velocity of light in medium 2 upon velocity of light in medium 1 is what is the notation. And that's what we have to do it. So in this previous example, as we had discussed, we have used the same mediums, medium 1 to medium 2, and then light was incident in exactly opposite direction following the same path. So in such examples, we can clearly see that the refractive index of 1 to 2 is 1 upon reciprocal, we can say reciprocal of 2 to 1. Refractive index of 1 to 2 is reciprocal of refractive index of 2 to 1, or we can say refractive index 1 to 2 is equal to 1 upon refractive index 2 to 1. Like here we are the air glass medium. So refractive index of glass with respect to air is equal to 1 upon refractive index of air with respect to glass. So here we see to study refraction, we take the help of lens. Like to study reflection, we used to take help of mirrors. Like there are mirrors, there is a plane mirror, exact straight, and there are mirrors which are spherical in shape, like the concave mirror and the convex mirror. Okay. Now mirrors work on the principle of reflection, so they don't allow light to pass through it. Whereas lens are transparent objects and therefore they allow light to pass through them. Okay. So here you see that whenever there's a bulge out, it is called as convex. Whenever there's a bulge in, okay, where there's a depression, okay. So cave means depression, they are dented in, therefore it's a concave. Convex lens, this is how it looks below, and concave, this is how it looks. Okay. When you touch it, you will find that you'll find this type of impression which is created. When you touch these lenses, this will be seeming to be bulge out and this will be bulging in. The center of the lens is known as the optical center. Please remember, either it will be denoted by C or O. Whereas C was center of curvature in a mirror case, here we use center of the lens. Either O, either it is called optical center O or the center of the lens C. Okay. What will be the principal axis? Principal axis will be going like this. It's the axis which divides the lens into two equal parts, above and below. Okay, that will be the principal axis. We'll see it again. Okay. So here is the figure to denote that a convex lens. Convex lens is a converging lens. A convex lens converges a parallel beam of light rays to a point F on its other side. Please remember it's lens. Therefore, it will allow light to pass through it. And since it is a convex lens, which is a converging lens, all rays, parallel rays of light passing through it will be converged to one point called as the focus on the other side of the lens. Light rays are coming from the left side and the conversion is taking on the right side after passing through the lens. Okay. And this is our concave lens. We can see again parallel beam of light, parallel rays of light incident on the concave lens, and it's a diverging lens. So we can see that the rays which are coming parallel, and we see that they are getting diverged once it passes through the lens. But the unique thing is this diverged rays, if you extend them back together, and before the lens we show it by dotted lines. Okay, these were proper lines after the lens. But then when we extend them back using dotted lines, all of these lines converge at one point, which is called as focus. This focus for a concave lens is on the left side, that is before the lens, and therefore we'll be seeing in the sign conventions later for solving the numericals, the focus being on the left side of the concave lens, we take f as negative, and in the previous example or previous convex lens, the focus being on the right side, okay, we call it as the focus is on the positive side, or the we take focus as plus. The next important point is how do we get a systematic position of the image? What type of images are formed? For that, initially we need to study the rules for obtaining images formed by convex lens. These rules we are going to study about the behavior of the convex lens on the incident ray of light based on the type of incident ray of light. Like case 1, this is a ray of light which is parallel to the principal axis. Case 2, this is a light ray which is oblique and directly incident on the center of curvature, or we can say center of the lens or the optical lens. And this is the again an oblique ray which is passing through the focus and incident on the lens. So three different cases. Case number 1, we see that a ray of light which is parallel ray, parallel to the axis, principal axis, the ray gets bent from the convex lens to the focus, passes through the focus and goes out. When a ray of light is incident directly on the optical center, we find that there is no refraction taking place. It goes undeviated in the same straight line, in the same angle. It continues. Therefore, AC extends as CY along the same line. Basically, ACY are collinear. The third case, when a ray of light is obliquely passed through the focus. Okay, this focus is before, saying that this is the second focal point, exactly at the same distance before the lens as it would have been after the lens. So if a ray of light is passing through the focus and gets incident on the convex lens, this convex lens makes it sure that it is bent and it passes the ray of light parallel to the principal axis. So if the incident ray of light was parallel to the axis, it gets bent and passed through the focus. If it is if the oblique ray is passing to the center directly, then the convex lens allows it to pass undeviated. And if the ray of light is incident obliquely passing to the focus on the lens refracts it in such a way so that it becomes, and bends it in such a way so that it becomes parallel to the axis. So this we can think of as the three rules which we can use it for finding the position, the nature of the images for different, from different positions of the object. For different positions of the object, where will be the image formed? We'll be using any two of the three rays at a time for getting the ray diagrams correct. So in a convex lens, we have 6 ray diagrams to be studied based on the position of the object. Object can be placed between C and F dash. It can be placed at the focus, between F dash and 2F dash, at 2F dash, between 2F dash and at infinity. Relating to the diagram, yes, case 1 we can have between C and F dash and at F dash, between F dash and 2F dash, at 2F dash, beyond 2F dash, and at infinite distance from the convex lens. We see if you are able to relate, then it looks like the similar to concave mirror case. So in concave mirror also we had 6 positions of the objects for which we had to study the formation of images. So we have 6 cases under convex lens here, and there will be 2 cases under concave lens. So the 6 cases under convex lens. The first case, we can see the ray diagram over here. As I mentioned, just in the previous slide, we saw how the convex lens creates its working. Okay, the working of the convex lens for different types of rays. So any two of them we will be using. Here basically the object represented by an arrowhead, okay, placed between F dash and C. Okay, so one is the parallel ray of light parallel to the axis, and another is a ray of light which is oblique ray directly passing through the optical center. So we apply the rules to understand it. So as for the first case, AD parallel ray of light parallel to the principal axis, a convex lens bends it to the focus. That is first one. Second case, when a ray of light obliquely incident at the optical center, it allows the ray of light pass undeviated, so CY continues. Now we find that the image is not being formed because these two lines AY and DX are not cutting each other on the right side of the lens. So what we do is now we extend back these rays, DX extended back up to A dash, AY extended back, and we find that this AY ray, when extended back, it meets the first ray. DX extended and AY extended meet at a point A dash, and this point we'll get the height of the image at this point, and taking a perpendicular, draw a perpendicular line at this point A dash. So from A dash to B dash, this will be the height of the image, or we can say the position of the image and how the image will look. We can see that the image is being formed on the left side of the lens, that is before the lens. When an image is formed before the lens, it is called as virtual image. Okay. Actually, the image should have been formed on the other side. A lens is a transparent object. So definitely when ray of light is incident on the lens, it allows the light to pass through it. Therefore, most of the time, the image has to be formed on the other side of the lens. So if an image is formed on the other side of the lens, it is called as real image. But in this particular case, we saw that the rays were not merging together or not intersecting together. In fact, these two rays were diverging, and therefore we extend it back to find that it converges on the left side of the lens, and that indicates the position of the image. And the position of the image being on the left side of the lens, the image formed is called as virtual image. We find that the virtual image is always erect, and in this case it is magnified also. Let's go to the other cases. The case when the object is kept at F itself, the focus on the left. So again, we take two rays. One is the parallel ray, another is the oblique ray passing to the center. We can say parallel ray, it just passes to the focus after bending, and the oblique ray which passes to the optical center goes undeviated. In this case, we see that these two rays, DF and CY, are exactly parallel to each other. They never try to meet, or we say they will meet at infinity. So here the image is formed at infinity, but it is formed on the other side of the lens, and therefore the image formed is real, and it will be formed below the axis. Therefore, it will be inverted, and it will be enlarged, highly enlarged case, but image is formed at infinity. Image is formed at the infinity, but it's formed on the other side of the lens. Therefore, real. It will be formed below the principal axis. Therefore, inverted, and it will be large in size. Therefore, highly enlarged. Now we shift the object little more left before the focus between F dash and 2F dash. When the object is kept between F dash and 2F dash, again the two rays being same, two rays for studying. One ray of light parallel, another the ray of light passing to the center. And what we see is after passing to the lens, the parallel ray of light bends through and passes the focus, and the another ray of light which is incident on the optical center goes undeviated, and both of them meet after some distance beyond 2F, and we see over here inverted image, comparatively larger than the size of the object, therefore definitely enlarged, magnified. Okay, since it is inverted, therefore we call it as real image. Why it is called real image? Because on the other side of the lens, it follows the rule that being transparent, the image is formed on the other side. Therefore, it is called real image. It is below the axis. Image is formed below the axis. Therefore, it is inverted. It is larger in size compared to the object. Therefore, magnified. Then we place the object at 2F dash, and we find that again the ray of light parallel and the ray of light oblique passing to the center. The rays converge at 2F. But the converging point is below the axis. Therefore, we'll get inverted image, and the size of the image will be the same as the size of the object. And since it is formed on the other side of the lens, therefore real. So the image is real, the image is inverted, the image is real, the image is inverted, and is of the same size of the object. And the object is placed beyond 2F, again parallel ray of light and light passing to the optical center, they meet, and they meet at a point. When you project it on the principal axis, it is found before 2F. Okay, so when object is kept at 2F dash, then image is formed at 2F. object is placed beyond 2f dash, then the image is formed between f and 2f on the other side of the convex lens. Again, real inverted, and but in this case, the image size is getting diminished. In this case, the image and the object were of the same size. An object is kept at 2f dash, image is formed at 2f, the image size was equal. When it was placed between 2f dash and f dash, the image size was inverted and enlarged. And when you keep it before 2f dash, you get a diminished image. And there's a last case when object is at infinity. The rays of light that we are taking, both the rays of light we are taking it as oblique, one passing to the optical center, one passing to the axis of the lens, and they both, what will happen? They'll both will bend. Actually, the light passing to the optical center will never bend, so it will directly pass undeviated. But the ray of light which is passing the axis of the convex lens, that gets bent and it touches or cuts the undeviated ray at the focal point. So you will extend AC up to A dash, which is just above or just below the focal point. And at this point, you can pause and the another parallel ray will actually meet at this point A dash. So this is again, we see that it's a real image because it's formed on the other side of the lens. It is inverted because it is formed below the axis, and it is very small compared to the actual object, and therefore it is called highly diminished. So we see here 6 different cases for convex lens, and we also see 2 cases for concave. We'll be seeing that later. And we of course see here the uses of convex lens. They are used in spectacles, hypermetropia, long-sightedness, where a person is able to see distant objects, but near objects is unable to see. Generally, this is the defect which appears in a human eye for people when they pass 40s, they're in the 40s or when they cross 40. So this is a hypermetropia, which is long-sightedness, and they are not able to see the near objects. We use convex lens for rectification. It is used in a simple camera. It is used for magnifying glass, using microscopes, telescopes, light projectors. So many applications of convex lens. As I mentioned before about the sign convention there, all those distances which are measured before the lens are taken as on the left side and they're called as negative, taken on the right side or taken as positive. The optical center is the point of reference. So the point C is taken as 0 position, and any other position on the right are taken as positive, on the left are taken as negative. Therefore, the focal length of a convex lens, we all in the out of 5 out of 6 cases, we have seen that the image is formed on the other side. As a transparent lens, it allows light to pass through it, and therefore definitely the image has to be formed on the other side of the lens. Therefore, the focus is taken as positive for convex lens. And for a concave lens, it will be taken as negative. There's a lens formula, 1 upon V minus 1 upon U equal to 1 by F. The mirror formula was 1 upon V plus 1 upon U equal to 1 upon F. This is 1 upon V minus 1 upon U equal to 1 by F. V, the image distance, U, the object, and F, the focal length. There's magnification factor also, which tells us about the nature of the image formed, definitely about the size of the image formed. M is equal to H2 upon H1, height of the image upon height of the object. It's also given as V upon U, okay, image distance upon object distance. Very much similar formulas to mirror, but there will be a small change in sign. Like here, there's a negative here. Here in mirror, it was minus V by U. Here we see plus V upon U. So M is negative. That means it's a yeah, M is negative. Magnification is negative. That means it's a virtual image, because virtual image leads to yeah, height H2, H1, both positive means image and the object are both above the principal axis. And that means M positive means is the case of a virtual image. And when H2 comes negative, that means inverted image. H1 will be always positive because the object is always considered above the principal axis. H2 can be below and or above. In case of real image, H2 is we can say below. That means H2 becomes negative and M becomes negative. So M negative means a real image formation. And in case of virtual image formation, the virtual image is always real and erect. So the virtual image is always erect. And therefore the H2 will be positive. So positive upon positive will be positive. M will be positive means H2 is positive. That means in the case of virtual image.